There's a popular idea in biochemistry called the lock and key model. This is a model that explains how large biomolecules like proteins can respond to the presence of smaller substrate molecules. The idea is that proteins generally have these cavities on their surface, called receptors, that are perfectly shaped to accept smaller molecules fitting into them. But the trick is that the small molecule has to have the exact three-dimensional shape to fit inside the cavity. Otherwise, nothing happens. And when those small molecules do fit and bind, that causes a whole cascade of other effects that in many cases end up with some signal firing in your brain so you can experience it. This is ultimately why sugar molecules taste sweet, because we've evolved receptors on our tongue for those molecules. And why flowers smell as beautiful as they do, because there are receptors for those molecules in our nose. It's how many of our medicines heal us, and it's the search for these Goldilocks molecules that drives much of modern drug discovery. But to understand any of that, it's critical to understand and be able to predict the shapes of molecules. To predict the shape of a molecule, we're going to use the valence shell electron pair repulsion model, or Vsepr for short. In this model, as the name implies, what we really worry about are how do the electron pairs in the valence around atoms repel each other. Let's take a look at a Lewis structure as an example. This is formaldehyde. It's got a carbon atom, a couple of hydrogens, and an oxygen. Notice it's got a couple of lone pairs on the oxygen, a double bond joining the carbon to the oxygen, and a couple of single bonds as well. For this molecule, and for any molecule that we want to think about in terms of the Vsepr model, we need to define what the electron domains are. An electron domain is really any three-dimensional region of space where one or more electron pairs live together. So in this particular case, that could be a lone pair, that could be a single bond, or it could even be a double bond, realizing that although there are 4 electrons here, they're all flying in close proximity together to create the bond that is between oxygen and carbon. So in terms of electron domains, I have 1, 2, 3, 4, 5 domains in total. And why I want to keep track of these domains is because the Vsepr model says, quite correctly, that electron pairs should repel each other. So the electron pairs that are in the valence of these atoms, or the outer regions of these atoms, should want to remain as far apart as possible. And so the exercise here is imagining how, say, a carbon atom should orient its domains around itself so that each of them remains as far apart from each other as possible. So really what we need to do here is, using a Lewis structure, count the number of electron domains that we need to place around a particular atom. And then, based on that, we can determine what the three-dimensional arrangement of those electron domains have to be in order to minimize repulsion between them. And the good news is that we only generally need to consider about 5 different options for what to expect. Central atoms generally have anywhere between 2 and 6 electron domains distributed around them. So we'll just need to spend a little bit of time with each of these options to understand the different outcomes. For atoms with 2 electron domains, we can fairly easily imagine how they would be distributed. A central atom can keep those 2 electron domains as far away as possible from each other by simply placing them on opposite sides of its nucleus. This creates a linear structure, and that's exactly the name given to both the electron domain geometry and to the molecular geometry that would adopt that structure as well. And if I wanted to be really clear about what the angle is between each of these electron domains, it would of course in this case be 180 degrees. An example is carbon dioxide. Now we've done this Lewis structure in class, but as you can see here, this is a three-dimensional model of this molecule, and clearly each of the oxygen atoms are on entirely opposite sides of the central carbon. So we would call this a linear geometry. Now moving on to 3 electron domains, adopting a configuration as shown here is the best way, geometrically speaking, of keeping each of those 3 domains as far away from each other as possible. Because the shape that is made by doing this is a triangle, and each of these 3 domains lies in the same plane, the name of this electron domain geometry is trigonal planar. And here's an example of a molecule that adopts that particular shape. We're also looking at a 3-dimensional model here. Again, we can see that each of these outer atoms lie in the same plane as the central atom. And again, this is why we refer to this structure as trigonal planar. However, with these 3 electron domains, there is another alternative given here. It's of course possible that this molecule has one of those electron domains as a lone pair and not a bonding pair of electrons. And there are plenty of molecules that do in fact adopt this configuration. So we have another naming convention for these particular structures, and that is known as the molecular geometry. So the electron domain geometry is of course trigonal planar, as shown here. But the molecule itself, the molecular geometry, is often labeled according to where you find atoms. And so if we look at the atoms in this particular example, they adopt a bent structure. And the reason they adopt a bent structure is, of course, because there's a lone pair here in that other 3rd electron domain that pushes against this bond and repels each of those B atoms in this particular example, causing the overall network here to be bent. And so if you have a trigonal planar electron domain geometry, depending on the number of bonding domains versus non-bonding domains, you can have either a trigonal planar molecular geometry or a bent molecular geometry. And so the angles that we observe between adjacent electron domains in a trigonal planar structure are, as you might guess, 120 degrees. And you can predict that based on geometry. There are three points in a plane that are equally spaced, and so 120 degrees between each of them adds up to the full 360-degree circle. But there is an adjustment that we have to make to this angle in cases where we have the bent molecular geometry. You see, the electron domain that is the lone pair actually provides more repulsive force against the other 2 bonding domains than a bonding domain would have in the first case. So in a trigonal planar molecular geometry, we can generally assume that the angles formed between any of the outer atoms and the central atom is 120 degrees. But in the case of a bent molecular geometry, that angle is squeezed somewhat, and so it's less than 120 degrees, generally about 119. Moving on to the case of 4 electron domains, this is the first example that actually takes advantage of 3-dimensional space. This is known as a tetrahedral electron domain geometry, and it is geometrically the optimum way of taking 4 domains all attached to the same central atom and still keeping them as far apart as possible. You can actually investigate this structure for yourself by tying 4 balloons together at the center. You can arrange those balloons if you manipulate them in various types of ways, including even in a planar type arrangement. But really, any sort of shake or energy applied to that particular structure, and you'll notice that it collapses very quickly to its much more stable configuration, which is that of this tetrahedral shape. If we've got a scenario where all 4 domains are bonding domains, then we would say that the molecular geometry is also tetrahedral. And here's an example of methane we can see here as a 3-dimensional model. So this structure can be interpreted probably in a couple of different ways. One way is as a tripod, I suppose. So these 3 hydrogens on the bottom behaving like a tripod with one sticking straight up. This is a completely symmetrical structure, so I can manipulate this in any way and I get the same exact tripod on the bottom. So this is a perfectly symmetrical, and the angle between any 2 of these bonds or any 2 of these electron domains in a perfect tetrahedral is exactly 109.5 degrees. So 109.5 degrees between any and all pairs of these bonding domains. Now, another way to interpret a tetrahedral structure like this is potentially as a couple of interlocking V's. So I've got this V here at an angle of 109.5 degrees. And then just below it, I've got yet another V. So another one here underneath, also at an angle of 109.5. So this is the tetrahedral structure. Now, if I take one of those bonding domains away, so let's imagine that in this position now there is an electron pair. This would be analogous to, say, ammonia, NH3, where ammonia would have another electron pair here. My electron domain geometry in this particular structure is still tetrahedral. I have electron domains in 4 different places. So anytime I have 4 electron domains, my electron domain geometry is still tetrahedral. But my molecular geometry I can see is very different in this particular case. I'm missing one of those 4 bonding domains. And I label molecular geometry according to bonds, according to bonding domains. So the shape that we're looking at here is known as trigonal pyramidal, because this structure really does make essentially sort of a pyramid, right? So this is the bottom of the tripod we were talking about before. So this is a molecular geometry known as trigonal pyramidal. Now the angles that I would expect to observe in a structure like this, traditionally or under normal circumstances in a tetrahedral structure, these would be 109.5. But let's not forget that the added stress of the lone pair on top here that would be pushing down on all of these bonding domains underneath actually squeezes this bonding domain just a bit more, squeezes it by about 2.5 degrees. And so instead of being 109.5, in molecules like ammonia, this angle ends up being about 107 degrees. So being a little bit squeezed due to the presence of this lone pair up at the top. Now the 2 electrons in that lone pair up at the top are obviously closer to the nucleus than they would be if they were stretched out within a bond to another atom. And so it's really because those 2 electrons are so close that they actually provide more repulsive force against the other bonding domains than what a typical bonding domain would have. Now, removing one more of these bonding domains and translating it into a system now that still has 4 electron domains. I'm just supposing that this bonding domain is being replaced by an electron pair. So now 4 electron domains, but we don't necessarily see all of them. We see the bonds if we're imagining what the structure of the molecule looks like. So if we take a look at this structure now, this would be analogous to, say, the water molecule, OH2, where O would still have 4 electron domains around it. In this case now we've got 2 electron domains on the top of this oxygen atom, and we've got a situation where we've got a bent structure. So that's the molecular geometry for a system with 4 electron domains, but 2 of those are bonding. So this is called a bent structure. And if I had to figure out what the angle is here, again, typical tetrahedral, which the electron domain geometry here is tetrahedral, we would expect this to be 109.5 degrees. But again, this angle is being squeezed by the lone pairs, now 2 of them, that are on the other side of this atom. And so you again get another, say, 2.5 degree compression of this bond due to the lone pairs up at the top. So we started out at 109.5, then we got compressed as we went to 3 bonding domains. It was about 107, and compressed further, this is probably about 105 or 104.5 degrees here for the water molecule, or other systems with the same type of structure. All right, let's take a look at what 5 electron domains looks like. This is arguably the most interesting case here. I've brought up a 3-dimensional model, and I've color-coded each of the bonded domains in this particular case just to point out a really key difference for you to understand. In the purplish color here, or that lavender color, we're noticing 3 bonded domains. And then in the green, we're noticing 2 others. And I think you can see there's a clear difference between these. These are symmetrically non-equivalent. So if you look along the greens, you can see that they go straight through the central atom. However, if you look at the purple ones, they form a trigonal planar arrangement around the central atom. And if I look along one of those bonds, I cannot see straight through. So these are symmetrically different. Even if they were all the same color, I would be able to identify which 2 went straight through the central atom and which 3 did not. So we have different names for these different positions. The green positions here are what are known as axial positions because they form an axis straight through the central atom. The purple positions here are what are known as equatorial positions because you can essentially think of them as forming an equator around the center of this central atom. And the geometries around these various positions change importantly because of that. So we can see that the angle between any equatorial position and axial position is 90 degrees. They cut straight at a right angle there. The angle between any 2 equatorial positions is, however, 120 degrees, just like in the case of a trigonal planar molecule. And so this shouldn't be surprising to us because we know that a trigonal planar system has angles of 120 degrees between them. But this is, again, the most stable way to arrange 5 electron domains around a central atom while keeping them all as far apart as possible. Again, the key here being that there are actually 2 different types of positions. So the name we would give to this geometry is trigonal bipyramidal. All right, so trigonal because we've got these 3 equatorial positions, pyramidal because they form a pyramid, if you will, between the top of an axial position down to the equatorial positions creates a pyramid with 3 sides, so we call it trigonal pyramidal. But there's a bipyramidal because, of course, we'd have a pyramid on the top and a pyramid on the bottom. Right, so this would be a trigonal bipyramidal structure. So that's the electron domain geometry for 5 electron domains, and it's also the molecular geometry if all 5 of those are bonding. But of course, we have to consider what happens when not all of them are bonding domains, right? If there aren't other atoms at the ends of those positions. If we have a different number of bonding domains versus electron domains, okay, so non-bonding domains. Imagine, so this molecule we're looking at here is just a simple model where we've got a central atom with 5 electron domains, all of them bonding. If one of them were not bonding, it's important now for us to consider what is the most stable place to put the non-bonding domain? That's a really important question because it'll completely dictate the structure of this molecule. If I remove one of these green atoms and have that be a non-bonding domain, I'm left with a structure that would be essentially like a pyramid with a triangle around it. So we might call that triangular pyramidal or something like that. Or trigonal pyramidal. But if I remove one of these purple ones instead, I would have a very different structure. I mean, this thing would look fundamentally different than the other alternative. And so I really need to consider which option is best. And we can look at the table to understand which option is actually best, and that's an equatorial position. In other words, if I have to choose between an axial position to put a lone pair or non-bonding domain, or an equatorial position to put a lone pair or non-bonding domain, the equatorial position is always the more energetically favorable option. And the reason is fairly straightforward. If I look at one of these green axial positions, I can see that there are 90 degrees between that green position and each of the equatorial positions. So there's a lot of close contact, if you will. If I compare it to one of the equatorial positions, there are only 2 close contacts at 90 degrees. The others are actually farther away. So the other equatorial positions are farther away than this what would be a non-bonding pair here. And so there is essentially more three-dimensional flexibility here in the equatorial positions. And so if we have a scenario where we've got 5 electron domains, one of which is non-bonding, we can be reasonably sure that that one non-bonding domain will be in an equatorial position. And that pattern will continue on. If we have 2 non-bonding domains, they would be in 2 equatorial positions. 3 non-bonding domains would be in 3 equatorial positions. In other words, as we have more non-bonding domains in a 5 electron domain system, those non-bonding domains occur around the equatorial positions. And so these create different structures with different names. A single electron domain being a non-bonding domain, so suppose it's just this one, leaves us with this structure that's got sort of this V shape here, but then a straight line through it in the axial positions. We actually call this a seesaw structure. And you can imagine why, because this actually looks like a seesaw that could potentially go back and forth. A second non-bonding domain being added here would leave us with, if we look at this particular structure, imagine these 2 bonding domains were removed and only this one was left, we would be left with a T-shaped structure. So that's the name given to that. And then finally, of course, if all 3 equatorial positions were replaced with non-bonding electron pairs, the resultant atoms would just be the green and the central purple one here, and so this would just be a linear structure. And so these are the results of what you would expect, with the structure or the three-dimensional shape of a central atom that you would expect, with 5 electron domains having various or varying numbers of bonding versus non-bonding domains. Now, I talked before about the angles here. This is 120, whereas these ones are 90. And again, the same story is true. If one of these is replaced with an electron pair or non-bonding domain, that does add a little bit of extra force on the other bonding domains. And so I might not expect a complete 180 here. The angle underneath from this green atom to this green atom would probably be a little bit less than 180 because it would be squeezed more or less by the non-bonding pair here. Likewise, the angle between each of these 2 purple equatorial positions here would likely be less than 120 because of that lone pair. All right, and our final case for the day is that of 6 electron domains. This has a name of octahedral, which might be your first cause for confusion. Why, if I have 6 electron domains, do I call this octahedral? Kind of sounds like 8, right? Octahedral. That's really only because you would have an 8-sided shape if you were to connect all of the atoms here. If you were to connect all of the atoms on this structure and fill in a shape that would be formed by joining all those vertices, you would have an 8-sided shape. And so you can sort of tell that because let's look at these. I've got 4 atoms in the middle here, and if I drew a line from each of those up, from all 4 of those up to the top, I'd have a 4-sided pyramid, and then I'd have another 4-sided pyramid on the bottom, and so that's 8 sides. So this is called an octahedral shape. Now, despite the fact that it's got the most electron domains, which is 6 in this particular case, it's one of the easier structures to deal with because of its symmetry. I mean, you can see what's going on here. There isn't an axial or equatorial position here because it really doesn't matter how I look at this structure. All of those positions are entirely equivalent, and they're all 90 degrees away from each other. So what that means is that it's somewhat easier to interpret the kinds of structures I'll get when I've got 6 electron domains. They're octahedral, so this electron domain geometry is octahedral, and this molecular geometry in this particular case is octahedral as well. and there are 90 degrees between any two adjacent domains. So fairly simple due to its symmetry. Now the question still remains, though, is what would happen if some of these domains were non-bonding? So if I replaced some of these bonding domains with an electron pair. And the answer there is really that in the first case, it doesn't matter because of the fact that all of these domains are exactly symmetrically equivalent. You could take any particular one of them and replace it with a non-bonding domain. So suppose we were to replace this one here on what looks like the bottom. The remaining structure would have 4 domains around what you might think of as the equator right now, even though we wouldn't have called it that, and then another one remaining up here. And so this is a square pyramid, so we would call this square pyramidal. Again, noting that this bottom domain would have been an electron pair at that particular case. And at this point now, it is important for us to consider if we were to take another electron domain away, or I should say bonding domain, and replace it with a non-bonding domain. At that point, it becomes important because really this opposite end is the one that should be removed at that point. Because if I've got a lone pair down here, a non-bonding pair of electrons, we know that that imparts a little bit more repulsion onto the other domains than a traditional bonding domain would. And so if I'm going to put another lone pair on this system, best to keep it in the position that's farthest away. So those are really the two options. Removing one gives me a square pyramidal structure. And again, I might expect something less than 90 degrees between the remaining bonding domains because that lone pair is going to push up quite a bit on those others. But if I take a second domain away, and let's call this a non-bonding domain now, I'd be left with those 4 remaining, which as we can see makes a square, and so we call this square planar because all 4 of those are in the same plane. So those are my options here. And again, with a square planar structure, I would definitely expect a 90-degree angle here because there isn't anything squeezing it tighter. Really, my non-bonding domain up here and over here on the other side aren't really affecting the interatomic angle between these two. So that's really the summary there of the octahedral case, one of the more simple cases despite the fact that it's got many more domains.